This is level 2 of the CFA program, Quantitative Methods, and the reading on time series analysis. Many candidates find this reading quite a challenging one, and it probably is. But I'm wondering if you don't think of it as a natural extension of what we've just finished in our readings on simple linear regression and multiple regression analysis, that it doesn't become a little bit more logical to you. Now, having said that, when you look at the LOSs, they don't pretty much look anything like what we had in the previous two recordings. Notice that we have to consider topics like covariance stationary, an autoregressive model, mean reversion, random walks, unit roots, heteroscedasticity, co-integration. And so clearly these LOSs are unique to time series. However, if you view a regression analysis as one variable trying to explain another variable, and in this case with a time series, what we're saying is that a variable yesterday can be used to explain a variable today, that same variable, so time series. So that's pretty much what a time series is, but we're going to be doing lots and lots of stuff that was very similar to our simple linear regression and perhaps even multiple regression. All right, so let's take a look at some of these initial LOSs. Let's go ahead and take a look at a time series and try to estimate a predicted value using both just a regular trend and maybe a log linear trend. And so just to start, look at the picture there of the relationship between time. So notice on the horizontal axis, we go from 2016 all the way out to, sometime in the middle of 2021. And this is really a time series of the performance of the US dollar and the euro currencies. And so clearly there are some trends over time periods. So look at the period between 2017 and 2018. There's an upward trend. And then the period between 2018 and 2020, excuse me, there's a downward trend. And then through the initial part of 2020, 2021, there's yet again another upward trend. So what we're going to do is say, is there a relationship between time and this particular variable, which is an exchange rate? And the answer is probably yes. And the answer is probably yes, comma, let's go ahead and try to figure out what the problems are associated with using a time series that we didn't quite face, or at least we didn't face with the magnitude back in simple linear regression. All right, here's a little bit of a review of what I just said. A trend is a sustained movement of a particular variable in a specific direction. Okay, it can be upward sloping, can be downward sloping as well. So let's look at a linear trend model. The dependent variable changes at a constant rate with time. So notice over on the left-hand side of the equal sign, there's the dependent variable. And then over next to the slope coefficient, the beta 1 is t, and that's for time. So time can be 1 and then 2 and then 10 and then 100 and then 1,000 if you have 1,000 data points. We still have an intercept term, we still have a slope coefficient, and we still have a disturbance or an error term as well. Here's a good picture, right? Blue line is upward sloping, red line is downward sloping, so those are linear trends. Now remember, when we use this simple linear regression, we're trying to throw a line at it, but if I go back to our exchange rate trend, clearly that's not a line going up. How about if I say a squiggly line? Squiggly, that's not a finance term, by the way. All right, look at that LOS. It asks us to calculate a predicted trend value for a time series. So look at the bottom there. We're given an intercept of 2 and a slope coefficient of 1.6. The predicted value of y after 4 periods, all you do is substitute 4 in there for t, and you do quick math, and you get that predicted value of y of 8.4. Now, sometimes an analyst might suspect that the relationship between time and dependent variable is not linear. Maybe it increases at an increasing rate, maybe it decreases at a decreasing rate, maybe it changes signs over time. And that's why we can use this log linear model. So look there over on the left too, it's increasing at an increasing rate. So those are examples of exponential relationships. And then you can calculate a predicted value over on the right-hand column there. You get the 8103. You do it exactly the same way we did in that previous slide. However, you need to hit your ln button on your calculator or your e raised to the x button on your calculator, and you get the 8103. Now, of course, you're probably thinking, all right, Jim, that's a pretty simple model, right? We're just using t, or taking the natural log, and we're saying time equals 1 and 2 and 8 and 15 and whatever that number is. Boy, I wonder how accurate that model is. And sometimes it is. Many times it's not. However, even if it's accurate, and especially when it's inaccurate, we have a big problem. Notice that we have a big old exclamation point over there on the right side of this slide deck. The error, so what are we calling this? Limitations of trend models. This is the last part of that LOS. The error terms may be correlated. And if those error terms are correlated, then we know that this throws everything out of any kind of a semblance of what we want to look like. So notice the third teardrop point. We call this serial correlation. Historically, in all of our linear regression analysis, the estimates are inconsistent and invalid. So think about what that means. You do all this work, you collect all this data, and you come up with some great conclusion, and then you say, oh, I wonder if those error terms are correlated. And if they are, then all that work goes flushed right down into the commode of life. Now, of course, one way to detect this serial correlation is through the Durbin-Watson test. We talked about this back in those previous two recordings. However, that's going to be an issue as we move through time series. All right, so if we have this concept of, here, let me go back here real quick. If we have this concept of correlated error terms, what can we do about it? What do we call it? So we come up with this new name, covariance stationarity property. All right, you ready for this? A covariance stationary property means that the time series, such as the mean and variance, are constant over time. All right, so look at the purple box in the middle. Expected value of the time series is constant and finite. The variance of the time series is constant and finite. And the covariance must be constant and finite. So we've got these strict properties to be covariance stationary. All right, so look at that last diamond point. If the time series appears to have the same mean and variance, oh boy, and we'll talk about seasonality here in just a little bit, but with no apparent seasonality, we may assume covariance stationarity. Which means then that our linear regression estimates are valid, and then we can make some inferences that have some reasonable economic meaning. All right, let's pause on that covariance thing that we just talked about. And let's go ahead and take a look at a model here. So here we have an autoregressive model. What we're saying here is that instead of the dependent variable being related to time being 1, 2, 3, 4, now we're saying that the dependent variable is related to what happened yesterday or last week or the day before with that same variable. I like to give sports analogies, so let's go ahead and say something like, hey, you know what? Suppose we're big LeBron James and NBA fans, and we want to come up with a model to predict and evaluate the relationship between the number of foul shots that he makes in the game today versus the number of foul shots he made in the game yesterday. So the model would be, yesterday's number of foul shots, say it's 8. And today's, let's suppose they have a game and he makes 11. And so the best predictor of today's number of foul shots that LeBron can make is yesterday. So look down under the example there. So an AR1 model, an autoregressive one model, is that the dependent variable xt is a function of yesterday's variable. So xt minus 1, notice there's an intercept term and there's a slope coefficient and there's still a disturbance term out there. So that's an AR1 model. So we might say something like, hey, the returns to a credit default swap yesterday, time period t minus 1, are a great predictor of what's going to happen today in the credit default swap market. And then, of course, you can go back 2 days or 2 weeks or 2 months, whatever it is. So look at the AR2 model. We're saying that the dependent variable xt, let's suppose that's today, is a function of what happened yesterday, t minus 1, and the day before, t minus 2. And of course, it could be weeks or months or years. And then look at the purple teardrop point down there. Longer interval differences can be used to account for seasonality. We'll have a pretty cool example later on in the slide deck. So notice there's on the right-hand side of the equal sign over among the independent variables, there's an xt minus 1 and then an xt minus 4. We're probably just assuming here that we're looking at quarterly data. So we go back 4 quarters because maybe there's seasonal data. I remember my economics professor, strange what you remember from your undergraduate days. I mean, this was 100 years ago, but I remember my economics professor using the example of snow shovels. And so you sell not too many of them in July, right? If you live here in northern United States, but you probably sell a lot of them in December and maybe January and February. So seasonality, that makes a lot of sense. All right, let's work our way back up. I skipped a couple of lines there. So P is known as the order of the model. So you could have an AR, you could have an AR 100, right? You could go back yesterday and the day before and the day before that, all the way back to minus 100. I'm not sure how appropriately modeled that would be. So P is the order and it indicates the number of lagged variables. Now, what we can do in these AR models is we can predict based on the estimated parameters from the model. So look at these, look at the one step ahead forecast. So there's our AR1 model, xt and xt minus 1. And let's look at this example. So let's suppose where we have the intercept is 2 and the slope coefficient is 1.8. Let's suppose that when that what we're looking for is when the variable x, whatever that is 2, that it's closest to, and then you get the 5.6 down there at the bottom. So you say 2 plus 1.8 times 2 is equal to 5.6. Now, what you can do then is you can do this chain rule. We can do this chain rule of forecasting, and we can go once again. So calculate the 2-step ahead forecast of x2. So we're going to do the 2 plus the 1.8. So those were given to us in the previous slide. And then we're going to multiply by the 5.6. Here, let me go back just quickly. So there's the 5.6 for our estimate of x1. And then here's our estimate of x2. So you can see why it's called, you know, some kind of a chain rule. You use one prediction to then estimate the next prediction. And so you get the sense of how this AR model moves through time. So if it was some value then and then and then, and I guess you could do in my example that I just gave a moment ago, you could do 100 of these things. But boy, if the CFA Institute asked you to do a 100 step ahead forecast, you probably should just guess. Boy, that's probably really bad advice, but how long would it take you to do 100 of those? All right, how about another LOS? Explain how autocorrelations of the residuals can be used to test whether the autoregressive model fits the time series. All right, so now we're back to covariance stationarity. We need to say to ourselves, all right, what's going to happen? Now, when we're using a time series, we use the term autocorrelation. It's still the same as serial correlation back in our previous examples, but we now switch over to autocorrelation term. Now what we're going to do is we're going to perform a test, and I'll show you that here in just a second. And look at the last diamond point there in purple. An accurately specified autoregressive model will have residual autocorrelations that do not vary significantly from zero. So once again, just like back in linear regression and multiple regression, where we're going to do some kind of a test. Remember, we did a t-test back in those days, and then we're going to have to get out a table and see if it's significantly different from zero. So the testing is going to be identical to what we did in those two previous recordings. So here's the procedure. So we're going to estimate the autoregressive model and calculate the residuals. Calculate the autocorrelation for the residuals. Now, the good news for all of us is that software does all of this for us. It's not like we're going to have to get out our calculator and 29 pieces of paper and do all of this stuff. All right, and then we're going to perform a t-test. That's what I was warning you about just a second ago. If the null hypothesis of no correlation is rejected, then the model is not correctly specified and should be modified. Failure to reject implies the model is statistically valid. All right, so here's our test statistic. We're going to have that autocorrelation in the numerator, and we're going to divide by the standard error. So all we're going to do is take, this is simplified with autocorrelations. The standard error is just 1 over the square root of time. We're going to have t minus 2 degrees of freedom. And so look in the numerator, there's that, there's the good correlation. So there's the autocorrelation. Notice it's the row, right? The sideways p. It's the correlation coefficient, if you will, between the successive error terms. All right, let's take a look at an example of how we can test for this autoregressive model. So there's our AR1 model. There's xt on the left-hand side. There's xt minus 1 over on the right-hand side. So this analyst collects 59 observations. There's our 5% level of significance, which is pretty common. And note that there's the output from the software for this regression analysis. So we're not going to have to compute any of these things. What we will have to do, however, is we will have to compute the test statistics. So notice that's the autocorrelations, which is in one column, and then the standard error, is 1302, 1 divided by the square root of 59. So take each one of those autocorrelations and divide it by the 1302, and you get the test statistic over there on the right-hand column. So look for a table on the exam where you either have the test statistic given or you have to compute it using the standard error. Now, this is a little bit different than what we did back in those previous recordings. Remember, we were given the coefficient and the degrees of freedom, and we had to do all that subtraction, division, and to get those test statistics. So you probably won't have to do that here. I did warn you we'd have to look up the table, so there's our table. We've done that multiple times. What did I say to you? 5%, the critical value is going to be somewhere around 2, right? Unless you have 3 observations. But when you have something greater than 40 or 60, it's going to be around 2. So look at that, it comes out to be exactly 2. So what are we saying here? The critical value is 2, and our test statistics, those are all under 2 absolute values, of course, right? And so notice the 2 arrow points implies that none of the autocorrelations of the residuals are statistically different from 0, and that the conclusion is that the AR model is correctly specified. So then we can go ahead and make some inferences based on this model. All right, how about this concept of mean reversion? I like to give sports analogies, and I've said this to you before in another recording. Maybe it was back in level 1, but I always think about this. when I'm watching golf. I'm a big golf fan on television, and one of these amazing golfers on Saturday in a 4-round tournament shoots a 61 or a 62 to get within one shot of the lead, and the next day the announcers always say, well, it's really hard to shoot a 61 or a 62 on Saturday and then do it again on Sunday. And I'm waiting for one of these announcers to say it's because of the reversion to the mean, and that's exactly what this shows here. Look at that upward slope, and so we've got squiggly lines around the upward slope. And so mean reversion refers to a time series behavior to fall when its values are above and rise when they are below. So the golfers who shoot 62 or 63 on Saturday are probably going to come back on Sunday and shoot, 68 or 70 or 72, right? Reversion to the mean. That mean reverting level can be expressed with that box over there on the right. The intercept divided by 1 minus the slope. Let's go ahead and take a look at a quick example here. Here's a model, explains the change in the unemployment rate over time and the mean reverting level. We've got the slope there, the intercept 0407. Divide that by 1 minus the slope, 5647, and we get 2.6%. Notice the LOS asks us to calculate a mean reverting level, so we just did that, 2.6, and then explain mean reversion, and so there's the interpretation. If the change in the current unemployment rate is above 2.6, then it's expected to fall in the next period, and then vice versa. How about if we compare in-sample forecast errors and out-of-sample forecast errors? This is really an interesting kind of a scenario. So I want you to think about this. So we have this model, and we come up with a regression output. And we can use that regression output to go back and say, okay, how well were we able to predict what happened on January 17th? And let's suppose that we'll go back to the LeBron James example of foul shooting. And let's suppose that we did January. So we collected data on every foul shot, every game, and number of foul shots that he made during every game. So we have this output, and we go back to January 15th. Okay, so we look at the data and we say, okay, on January 15th, LeBron made 11 foul shots. The model predicted that he was going to make 10.2 on that particular day. And we say, okay, maybe that's a pretty good model. So in sample forecast, that's what we're trying to do there. But out of sample forecast errors, now we're going to take our January model and say, okay, let's assume that LeBron has the same skill set in January and February. And, you'd have to make that assumption, right? I mean, LeBron, he's been playing basketball for 100 years, and so his foul shooting is probably not going to change between January and February, although there might be some minor variables that could influence this. But let's take the January model and try to predict what he does in February. And so we can look at the February data and say, okay, on February 15th, LeBron made 14 foul shots, and our model predicted, what did I say, January and February? I'm just going back to 10.8. Not that that would come out to be that way, but so the out of sample forecast errors are probably going to be greater than the in sample forecast errors because it's a different data set. Now, what we're trying to do here is decide which January model of LeBron's foul shooting is going to be able to predict the February of LeBron's, right? So remember, the problem here is that if we lived in a perfect world, we would be able to go out and collect all the data from LeBron's foul shots for his entire life. That would be the population. But we don't have the time or the energy or the resources to do all that. So we sample. And so what we want to do is we want to find the best sample. So look at the bottom right there, that last purple arrow point. Models are selected based on out of sample forecast error. So what do we want? We don't want to use a January model that's going to say on February 15th, LeBron's going to make 312 foul shots because nobody in the NBA has ever even shot 312 foul shots in a game, let alone make 312 foul shots in a game. So we throw that model out. So the question is, how do we do this? And we're going to do this using the root mean squared error technique. And this is super simple, and you'll see this in an example. we're going to calculate the residuals, we're going to square them, we're going to take the average, and then we're going to take the square root. And then we're going to choose the one with the smallest root mean square error. Here's a super simple example here. So suppose we have two calculations, 6.9 and 5.6, take the square root of the two. And so we're going to do the AR2 model in this case. So we're comparing an AR1 and an AR2 model, and that makes sense, right? We're going to say LeBron in that January model, we have one where it just takes the day before. And then in another model, an AR2, we're going to consider his foul shots the day before and then 2 days before. Maybe that's more accurate. Probably is. Sounds reasonable, right? Boy, we always have a problem with the stability of coefficients. So this LOS, explain the instability of coefficients of time series models. Well, this is pretty much true regardless of what kind of a regression model and relationship that we're looking at. But in particular, time series coefficients can be unstable across time. Of course, it depends crucially on the sample period selection. Also depends on the length of the sample period. When I wrote my dissertation, I collected 3 years worth of daily stock returns. And I remember I, came up with this solution, I came up with this conclusion, and I presented it to my dissertation chairman. And he said, Jim, this is all good work, but what happens if your beta coefficient is not stable? And I was like, well, I scratched my head and I said, well, you tell me what to do. And I think that was the end of our conversation. But if you have this big problem with instability of coefficients, then you got to figure out what is the appropriate sample period. So look at that. What is that? 1, 2, 3, 4. The fifth teardrop point. The choice of the model to be used in the analysis depends on the sample period. And that's why lots of financial analysts like to use, at least from this perspective, they like to use an AR2 model. But notice the bottom down there. There is no definite theory to determine the appropriate sample period. And that's probably why my dissertation chairman said, Jim, 3 years is probably okay. All right, how about some basic guidelines to determine a suitable sample period? All right, so avoid basic sampling theory, right? Do not use two clearly distinct populations, right? We don't want to say LeBron James' number of foul shots when he was an all-star in the NBA versus the number of foul shots he made when he was 5 years old and he could barely get the ball up to the basket, right? Two distinct populations. Do not mix stationary and non-stationary time series. Do not combine with series with different means and variance terms. All right, that makes perfect sense. The longer sample period is a sign that the sample probably, not definitely, but probably comes from different populations. All right, that all makes good sense. I think this is where candidates start to begin having challenges from a statistical perspective. So let's go ahead and start talking about a random walk and contrast them to our covariance stationary processes. All right, a random walk. Let's just skip down to the blue box. This is a random walk model. So xt is our variable today, and xt minus 1 is our variable yesterday plus a random error term. So notice that this is identical to what we just did with an AR1 model. And please note that I put the AR1 model in red underneath. But in the random walk model, we're assuming that there is no intercept term, right? B0, beta sub 0 is equal to 0, so that falls out. And we're assuming that the slope coefficient beta 1 is equal to 1. So notice that the B0 and the B1 fall out from our AR1 model, and it becomes the random walk model. So notice what we have inside of that gray box, that the best prediction of the random variable today, xt, is its yesterday's value. Like if LeBron made 10 foul shots yesterday, then maybe he's going to make 10 foul shots today. Of course, that probably depends on who's reffing the games and who LeBron is playing. All right, these characteristics are summarized in what I just gave you in that previous slide. So there's the intercept of 0. There's the slope coefficient of 1. So an AR1 time series is a random walk, assuming those two conditions, intercept 0, slope equals 1. Now, the expected value of the error term is equal to 0, and you can throw in a drift in there, and the random walk with a drift looks almost identical to our AR1 model. Now, here's the problem with a random walk. It has an undefined mean reversion level. Now, remember, there's our formula. Look under the arrow, the blue arrow point. There's our equation, beta 0 divided by 1 minus the slope coefficient. However, of course, in a random walk, our numerator is going to be 0. I mean, that's really not a problem, having 0 in the numerator of a ratio. But notice what happens in the denominator. We have 1 minus 1. And so 0 divided by 0, if you ever tell a math person, hey, 0 divided by 0, what does that mean? They're going to say, oh, that's undefined. Whatever undefined means, you can't divide by 0 because somebody in mathematics said that it's not possible. And it has to do with multiplication and division and all that kind of cool stuff. So, but look at the second purple diamond point. A random walk is not covariance stationary. All right, so this is important. This is super important. So we go back, let me just go back here. So we know that our AR1 models may or may not be covariance stationary, but now we know that a random walk is not. All right, so what this tells us is that the mean and the variance of a time series remain constant over time, but not in a random walk. And it's because the random walk process does not appear to have an upper bound. In fact, it does not have an upper bound. An upper bound. So look at the last, what is that, kind of reddish bullet point. This implies that we cannot use standard regression analysis on a time series that appears to be a random walk. And this has everything to do with this unit root problem. All right, so an AR1 series is said to be covariance stationary if the absolute value of the lag is less than 1, the lag coefficient. All right, so if it has an absolute value of beta 1 is equal to 1, hold on a second, let's go back here. Let's go back here. So what do we know? We know that in a random walk, beta 1 equals 1. So random walks have unit roots, right? Look at the third arrow point. All random walks have a unit root. All right, so here's the problem with random walks. The problem is because of this undefined mean reversion level. So they are not covariance stationary. We cannot apply standard linear regression for a test that beta 1 is equal to 1. So what do? Do we just, is it 4th down and 25 if we're playing football? And we just say, all right, let's punt. Let's just punt and give the ball to the other team. No, the answer is, hey, let's go ahead and perform this Dickey-Fuller test to establish if we in fact have our unit root, and then we can do some first differencing. All right, so first differencing, this is a fairly easy concept. Right, so all we're going to do is we're going to subtract the value of a time series from itself. Notice the bottom arrow point. A properly differenced random walk time series is covariance stationary with a mean reversion level of 0. So a properly differenced, all right, so here's the deal. What we can do is we don't have to punt. We can go and come up with a play and say, all right, let's do something different. And then the model can be used for appropriate inferences. And all we're going to do is this concept of first differencing. All right, so let's go ahead and do this unit root test for non-stationarity. So unit root test involves checking to see if the time series is covariance stationary. Two ways to do this. We can check for autocorrelations and we can carry out that Dickey-Fuller test. All right, then what we're going to do is we're going to estimate an AR model, an autoregressive model, do the t-test, do the residual autocorrelations, and then we're going to go ahead and perform that Dickey-Fuller unit root test to see if there are unit roots. All right, so here's this Dickey-Fuller test. So we got these steps down the left-hand column, and then the actual math over there on the right of transforming. So there's our basic model over on the right. xt, there's xt minus 1. So all we're going to do is we're just going to add something to both sides of the equal sign, which doesn't affect the equality, but in this case, we're going to subtract. So notice what we've done over there. We've taken xt minus 1 from the right-hand side of the equal sign, and we've subtracted xt minus 1 from the left-hand side of the equal sign. Then we do a little bit of algebra, and we get the transformed coefficient we're gonna give it a different name. We're gonna give it a different letter. We're gonna give it a different notation. So that coefficient, now you see up in step 2, the b minus 1, we're going to allow b minus 1 to equal g. So look on step 3, there is our first difference model. So we have xt minus 1. That's going to be our dependent variable. And then we're going to have xt minus 1 as our independent variable with the coefficient of g1. Everything else stays the same. Now we're going to perform a t-test. All right, so we're going to perform the test, and here's the null. And this is super important. This sounds like a great exam question to me. A test that g1, right, since it's first differencing, if g1 is equal to 0, this is identical to testing that the slope coefficient b1 is equal to 1, right? So there's our test for unit root. So make sure that on an exam you have this memorized, right? The null hypothesis in this DF test, g1 equals 0, is identical to b1 equals 1. Against the alternative that we know that we want it to be less than 1, right? So there's the alternative. The time series has no unit root if b1 is less than 1. All right, so what can we do? Step 5, rejection of the null hypothesis implies that the time series does not have a unit root, while failure to reject means that the time series does have a unit root. So now we might suspect that we have a unit root. We might suspect this AR model has a unit root. We might suspect that that we have a random walk, but this DF test tells us exactly whether or not we do. All right, how about seasonality? I mentioned this a bunch of slides ago. Remember we had that xt minus 4. So seasonality is a time series feature in which data shows regular and predictable patterns. What did I say to you? You know, snow shovels during the wintertime. That makes perfect sense. Yes, so seasonality is detected by autocorrelation when it differs significantly from 0. So this is going to be a cool example here. So let's do quarterly seasonality. So there's our AR2 model, right? B1 xt minus 1, and then B2 xt minus 4. And that the xt minus 4, there's our seasonal lag. So we're going to just do our regular old regression analysis and to test whether the seasonal lag will eliminate statistically significant autocorrelations. All right, so here's some output. Once again, it's so beautiful when you have output on the, remember you're getting a question stem that's going to be a vignette, so it's going to be a big old paragraph or maybe even an entire page, and you'll have these regression outputs. All right, so what's our example up here? An analyst performs a time series, found the presence of serial autocorrelation in the error term, decides to use the first difference log of sales to obtain a covariance stationary time series. All right, so we talked about first differencing and we talked about logs. So this is what we're doing. So we have, notice on the left-hand side of the equal sign, we have the natural log of sales today minus the natural log of sales yesterday. And then we're going to do the same thing over on the right-hand side of the equal sign, but we're going to go t minus 1 minus the t minus 2. So using quarterly returns, January of 2001 all the way through December of 2018. So boy, there's a bunch of time, right? What are we doing? This is all these time periods. So we got lots of them. Look at our number of observations. There's 74 under the regression statistics. And we're given coefficients and standard errors and test statistics. So look at the bottom left. Test for seasonality in the time series and suggest how to correct it. All right, so we're given that intercept and the slope coefficient. There's our standard error. There's our t statistic. And then autocorrelation. So what are we seeing there? Look in the bottom right column under test statistic for autocorrelation. So we have 0.15, we have 0.33, we have 0.24. And what did I say to you earlier? You know, that critical value is probably going to be somewhere around 2, right? The observations are 74. But now in that lag of 6.58 of a test statistic, oh my word, that's going to be bigger than 2. So let's get out our table again. There's a table. We've seen that bunches of times. So what did we have? We had 74 observations. So boy, does it really matter? Does it really matter if you do the appropriate t-2 degrees of freedom? You memorize that and make sure you have it. But with such a large t statistic there, 658, doesn't really matter how many degrees of freedom there are. All right, so what does that say? Degrees of freedom, that gives us 1.99. So of course, what we're going to do is we're going to say, oh my goodness gracious, right? 6.59 is greater than 1.99, but the first 3 are not. So lagged 1 and lagged 2 and lagged 3. So none of those first 3 lagged autocorrelations is significantly different from 0. However, the fourth one is. Right? So we're going to reject the null hypothesis that the lag for autocorrelation is 0. That means there must be seasonality in the time series. That means we can't use it. The model is misspecified. So how do we correct it? Well, what we're going to do is add a seasonal lag to it. So look at that LOS. How to test and correct for seasonality. So the answer to that part of the LOS is to modify it using a seasonal lag. So notice what we have. We still have the same thing over on the left-hand side, the dependent variable, but now we're adding a B2. We're going to say, let's go back to ST-4 and subtract ST-5. And what that will do is that will probably eliminate that regular quarterly pattern, if it does exist. It will probably, but of course you have to go back and test it and do all that other kind of stuff. How about the last part of this LOS, forecasting a value? This is super easy. This is what we've done before. Let's go ahead and look at some parameters that are given to us. So beta 0 is 0.008, beta 1 is a minus 0.65, beta 2 is 8.068. And so skip down, what are we saying here? If sales increased by 2% in the last quarter and 3.5% 4 quarters ago, the forecasted sales growth. So there's our model there. So that's, notice on the left-hand side, we're taking the difference between sales today and sales last time. So that's growth rate. So we just plug in all those numbers and we get about 3.5%. All right, how about the next LOS? We're trying to explain autoregressive conditional heteroscedasticity. Arch, remember we had this assumption that the variance of the error terms was constant. We did that back both with linear regression and multiple regression. Well, what happens if it's not? So we made the assumption that we had homoscedasticity, but now what if we have heteroscedasticity? Well, remember that throws off a lot of parts of the model. The standard errors of the regression coefficients are probably biased and any conclusions are invalid. And so what we need to do is we need to come up with, so look at that bottom teardrop point. These arch models, these are autoregressive models, right? AR1 or AR2 or AR100, and they're going to have conditional heteroscedasticity. All right, how do we test for conditional heteroscedasticity? I mean, all we do is regress the squared residuals from each period on the prior squared residuals. So notice I put this, we put this equation in some different colors. So what we're doing is there's our squared residuals in time period t, that's in red, and there are the squared residuals in time period t minus 1, that's in purple. All right, so this is just regular old regression analysis. And what we're doing is that we want to know is that slope coefficient, here we have alpha 1, is that statistically different from 0? If the series shows an arch 1 effect, since this is an AR1 model, then there is a need to correct for heteroscedasticity. Then we can predict the variance of the errors for the time period t plus 1. All right, so let's take a look at an example here. So here are the results from regressing the squared residuals on a constant, so there's the intercept, and a 1 lag of the squared residuals. All right, so there's our coefficients, 916 for the intercept, and 2050 for the residuals. There's the standard errors that are given in this output, and there are the test statistics. All right, so we're given 2 challenges here. Test whether the original time series has arch 1 errors at 5%, and then predict the variance of the next period. All right, so once again, we're going to get out our table. So what were we given back here? I forgot those number of observations. All right, 358. So we're going to do, this one here is just t minus 1, so 5%, so that critical value, oh my gosh, there it is, somewhere around 2, so it turns out to be 1.97, and what happens? It's 4.04. So this implies that the alpha hat is statistically significantly different from 0, and the time series has an arch 1 error. Now let me call your attention to the example in the actual CFA Institute reading. Their example goes through this problem, and this coefficient has a t-stat that's like, I forget what it is, like 0.9 or 1.1. So we fail to reject in there. So this is really good addition that what we've done here, we've shown you an example where we go ahead and show that we have arch 1 errors. The reading shows an example in which you do not. And then part B of this LOS is pretty simple, right? All we're going to do is if the squared error in the current period is 0.5%, so that has to be given. So all we do is take the 9.16, right? There's the intercept, and then the 2050, multiply that by the 0.005, which is the 0.5%. So the variance in the next period is going to be that 9169. All right, let's move on to yet another topic here. We're getting down to the end. We're getting down to the end of this slide deck. I promise you there's not 300 slides in this one. How about this concept of co-integration? All right, look at the example we give you. Consider a time series of the inflation rate regressed on a time series of interest rates. Oh my goodness. All right, so up to this point, we've had xt on the left-hand side of the equal sign and xt minus 1 and maybe some other things on the right-hand side. But now, I mean, that xt could be inflation or it could be interest rates. But now let's suppose we have 2 time series. That's where we have to bring in this concept of co-integration. When we have 2 time series, we're using 1 time series to predict or estimate or explain another time series. And so this is what you should be thinking. You should be thinking, wait a minute, Jim, didn't you teach us somewhere back in level 1 about correlation coefficients and covariances? Isn't that good enough? Why do we have to do something else? And let me go ahead and explain co-integration to you. I mean, what is covariance and correlation coefficient? Measures the magnitude and the direction of a relationship between 2 variables. Well, excuse me, co-integration takes it to another level, or maybe just a side level or a side layer. Co-integration measures the distance between 2 time series, and it measures whether or not that distance stays the same over time. So this is another layer, right? What did I say? Another level or another layer. So co-integration and correlation, they are related, but they're not identical, because you can have two variables that have zero correlation coefficient, but they are co-integrated because that distance remains the same over time. Now, not every day, but the distance on average remains the same over time, because those two variables, they could do this, right? They could move in opposite directions and kind of offset each other. All right, so that's the definition of co-integration. All right, so let's go back to the model. We have two different time series. The two series are subject to non-stationarity, just like they always have been. So we need to use this DF test to determine whether each of the time series is stationary or has a unit root. All right, so here are some outcomes. We'll have a couple of them. Both of the time series are covariant stationary, which means they do not have a unit root, which means you can use linear regression to test the relationship, and that means the regression coefficients are reliable, right? So if both time series are covariance stationary, that's super news, right? We can high five each other and say, yes, we have a great model. However, you know on the exam that the more interesting questions are going to be, let's suppose that one or both is not. All right, so if the dependent variable, if only the dependent variable is covariant stationary, then some, if not many, of those linear regression assumptions are violated. And in particular, the estimated regression coefficients and their standard errors are going to be biased and inconsistent. So remember that if the dependent variable is covariant, if only the dependent variable is covariant stationary, then you have a problem. If only the independent variable is covariant stationary, well, then you have the same kind of problems, but they're not as bad. If neither of the time series is covariant stationary, then we need to check whether or not the time series are co-integrated. All right, so look at this teardrop. This is what I was saying in that earlier slide. Two time series are said to be co-integrated if an economic or financial relationship exists between them, preventing them from diverging without bound in the long run. So was I telling you that the distance between them stays the same? So if they diverge, can you guys see me in my camera here? If they diverge, then they go way, way out. We can test for that using the Engel-Granger test or the Dickey-Fuller test. There we go. If both the time series are covariant stationary and co-integrated, then this is all good news, right? Hypothesis tests will be valid. All right, so my advice is to go back over these last couple of slides and say, this is a super important LOS. I think this is going to be super testable. I know I would test it. So just work through all of these things. And then, of course, you have to test for co-integration. So here we go. How do we explain co-integration? All right, so regress one variable on the other. So there's, look in the purple on the left, there's our regular old AR1 model. However, the AR1 model now has two different time series. That's why there's a YT on the left-hand side of the equal sign, right? So test the errors for unit roots using the Dickey-Fuller test, determine critical values, use the regression model to test the relationship between the two time series to see if they're co-integrated, and then make some conclusions. So look at the bottom there. If either one of these tests fail to reject the null hypothesis, we can conclude that the error term is not covariant stationary. Two series are not co-integrated, and then linear regression, any kind of inferences that we want to make are not going to be valid. So work your way through and understand covariant stationarity and then co-integration, and then the results of the conclusion of your hypothesis test. And I think this is a super helpful final slide. Choosing the appropriate time series model. Here's a step-by-step process. And this is pretty much a summary of what I have been covering, over the last 15 or 20 minutes. And so work through these. Boy, I would take a picture of this, have it on my phone, and just try to memorize all these things. Because if you think about it, each one of these steps, the yeses or the nos, are part of the learning outcome statements and are reasonable questions to ask inside of that vignette. And that takes us through all of that stuff. So notice covariance, stationary, autoregressive models, autocorrelation, mean reversion, right? Random walk, unit roots, seasonality, arch, co-integration. So the model ought to be in your brain as you're thinking about this. Start from the beginning and then work your way down all the way to the end. Start from the beginning, work your way all the way to the end, and then do it again and again. And I promise you that once you go through this, the first time you might go through it and get to steps 3 and 4 and 5, and then you'll have a question on step 6. So go back and do it again. I know you don't have 29 hours over the next day to do this, but just if you do this, I promise you, you can get it right.